Argentina is home to the largest Jewish community in Latin America, and one of the most prominent in the global diaspora. Approximately 175,000 to 180,000 people. Most live in Buenos Aires, where the community has played a central role in Argentina's cultural, political, and intellectual life for over a century. On July 18, 1994, a powerful bomb detonated outside the AMIA Jewish Community Center in Buenos Aires. 85 people were killed. Hundreds more injured. And the entire building was reduced to rubble. But it wasn't the first time. Just 2 years earlier, in 1992, a bombing at the Israeli embassy claimed 29 lives. The AMIA bombing marked a devastating escalation. And forensic scientists were called in, not just to sift through debris, but to decode the chemistry of terror. AMIA 1994, Forensic Chemistry and the Search for Truth. The device and its composition. The bomb was planted inside a white Renault traffic van. It contained approximately 275 kilograms of ANFO, a mixture of ammonium nitrate and fuel oil. ANFO is widely used in mining and demolition, but also by terrorists. Why? Because it's cheap, easy to acquire, and incredibly powerful. But ANFO isn't sensitive to heat or shock. To detonate, it needs a high explosive booster, typically RDX or PDTN, and a blasting cap to set it off. The blast pattern in Buenos Aires showed all the hallmarks of a well-balanced ANFO explosion. Moderate brisance, high gas volume, and a shaped charge effect, intensified by the building's layout. Chemical residues and forensic confirmation. After the blast, forensic chemists began a meticulous process. They examined debris, soil samples, concrete fragments, looking for chemical residues. Further examination revealed partially reacted prill particles embedded in the debris. These particles matched the texture and morphology of fertilizer-grade ammonium nitrate, confirming its use in the explosive charge. The incomplete reaction of some prills also pointed to partial combustion, a signature of how the explosive functioned during detonation. In addition to the inorganic residues, hydrocarbon compounds in the diesel fuel range were detected. Specifically, carbon chains from C10 to C20 were found on metal surfaces and within the blast crater. These hydrocarbons are characteristic of fuel oil, further confirming the use of an ANFO mixture as the main charge. Together, these findings confirmed that the main charge of the AMIA bomb was ANFO. But ANFO alone isn't enough to explain the explosion. Something had to ignite it. The RDX connection. Tracing the detonator. To trigger ANFO, you need a booster. And in this case, forensic science pointed directly to RDX swabs and material samples, labeled Q46, Q69, and Q72, were sent to the FBI Explosives Unit in the United States. There, specialists applied GCMS and FTIR spectroscopy. The results were conclusive, trace levels of RDX were present. No PETN. No TNT. Only RDX. That means a booster charge, likely RDX, was used to initiate the ANFO. While no detonator fragments were found, the evidence suggests a non-electric burning fuse was used. This type of fuse offers a simple time delay and leaves minimal forensic trace. But how exactly did scientists confirm those traces of explosives? To answer that, we need to look at the analytical techniques used then, and how they compare to those used today. In 1994, forensic experts relied on several established chemical tools. For ammonium and nitrate ions, they used colorimetric spot tests like the Grease and Nessler reactions, as well as ion chromatography. For RDX, the FBI employed gas chromatography, mass spectrometry, and infrared spectroscopy. These methods allowed them to detect even trace amounts of the booster explosive on samples from the crime scene. By contrast, in 2025, these tools have become more refined. We now use high-resolution IC/MS, LC/QT/OFMS, and ion mobility spectrometry for higher sensitivity and faster field detection. Even so, the techniques applied in the AMIA case remain the scientific backbone of modern post-blast forensics. Science versus obstruction, the legal struggle. The chemistry was clear. But the investigation was not. Despite strong forensic findings, judicial delays and political pressure obstructed progress for years. It wasn't until 2006 that federal prosecutor Alberto Nisman presented a comprehensive, 900-page indictment. He concluded that the attack had been ordered by senior officials in Iran and carried out by Hezbollah operatives. This was later supported by Interpol red notices and international legal rulings. In April 2024, Argentina's Supreme Court officially classified the AMIA bombing as a crime against humanity. It held Iran and Hezbollah responsible for planning and executing the attack. Lessons from molecules. The power of forensic chemistry. From nitrate ions to hydrocarbon chains to trace levels of RDX. This case illustrates the power of forensic chemistry to speak, even when others are silent. Although the bomb's composition was chemically typical, not unique to any group, the molecules told a consistent story. Science revealed the how, and helped lead to the who. It was analytical chemistry that reconstructed the sequence. Chemical evidence that confirmed the materials. And molecular data that refused to be buried. The AMIA bombing remains a landmark case, showing how chemistry, intelligence, and justice must work hand in hand. Chemistry doesn't lie. In every crime scene, every explosion, every act of destruction, there are molecules left behind. This is forensic chemistry. This is truth at the atomic scale. Subscribe to Chain Reaction, Root Cause Investigation for more real-world cases decoded through science. Like, share, and comment to help others understand how chemistry becomes justice. And follow my channel as I continue revealing the hidden layers behind the world's most complex investigations. Thank you for watching. Goodbye.